And yeah, I'm very pleased for this afternoon session to introduce Tashi Walde from Technische Universität München. And he will speak about higher Segal spaces via higher excision. Please go ahead.
Yeah, thank you very much for introducing me. And I would also like to thank the organizers for giving me the chance to speak at this nice event. Yeah, so I have very briefly outlined here the structure of this talk. So I'm going to start with something very basic, which are ordinary Segal spaces, which hopefully most are familiar with, but I will quickly recall. And then I will also say how one extends these to two Segal spaces. Then I will tell you how one introduces the hierarchy of higher Segal spaces in general. So this will be this part 2, and then will come somehow the actual meat of the talk, which will be about higher Segal spaces via higher excision, which I will motivate by some sort of manifold calculus on delta. Where here these quotes are very important because this is more like an informal analogy than actual honest math. But it's nice to have in mind. So yeah, so let me start with some recollections about classical Segal objects. So for me, delta is the category of finite, non-empty, linearly ordered sets, and the objects are each object is isomorphic to one of this form, but not every object is necessarily like this. This might be convenient sometimes. And so the key observation for our purpose here is that looking at simplicial sets, so functors from delta up to set, one can encode categories or monoids by the so-called nerve construction, which we have already seen in some version various times, where we take some category or a monoid or whatever, so some other structures, and we form a simplicial set by mapping out of all possible simplices. And the point is that this is fully faithful functor whose essential image can be characterized by the so-called Segal condition, which I have highlighted here. So a simplicial set is Segal if the value at, so this is my notation for the value of x at this object n, if this value is isomorphic to the following fiber product of copies of x at 1 over x at 0, where this map is induced by all possible inclusion of adjacent elements I minus 1 and I into n. So this is hopefully familiar. So let me just recall how one can recover the category C from its nerve. So this is done as follows. So assume we have an X. Assume we have, let me scroll down on this side. Assume we have such an X, then we can recover the associated category C by saying that the objects are the value of X at 0. So this is a set. The arrows are the set of X at this ordinal 0, 1. And then we have the source and target maps, which are induced by the inclusion of 0 into 0 and 1. And then there's this nice way of getting a composition where we can look at this span of maps here. So we have this triangle, and we can project either to the first and the second arrow or to the long arrow at the bottom. And by the Segal condition, this first map is an isomorphism, so we can invert it, and then this composite will give us the composition in our category. And here I'll put, let me put it on this side, I'll put this diagram which shows what the associativity means. I'll leave it up so you can contemplate it, but essentially so the fact that this diagram commute will tell us that if we go along this way, which will be one possible way of taking the composite, it will be the same as going along the other way. I'll leave this diagram up, and this will be somehow relevant once we move to two Segal spaces. Yeah. So now there's this well-known procedure, which has already also been mentioned in various previous talks, that we can pass from sets to homotopy theory by replacing the category of sets by some version of doing homotopy theory. So you can either use an infinity category or a model category, depending on what you're more familiar with. So I will be using infinity categories, but this doesn't really matter for this talk. Yeah, and so C will now be some favorite such homotopy theory like groupoid spaces, spectra, even infinity categories if you want, or whatever else. And then the idea is that if we have a simplicial object like this, so a functor from delta up to C, then we can evaluate X on any simplicial complex or even set, even though we're mostly going to be looking at simplicial complexes, by the following homotopy right Kahn extension, where we evaluate X at some simplicial complex, for instance, like this, by decomposing the simplicial complex into simplices and then gluing the values back together with suitable homotopy limits. So I will no longer say homotopy limit in the future. This will be implied. But, yeah, let me just focus it on emphasizing this point. And so this would be somehow the general formula. So if we have some general simplicial complex or simplicial set, we can always write it as some co-limit of representables, and then we just sort of pull this co-limit out and define the value as this homotopy limit. And now comes, and now we can sort of mimic the same definition and say that a simplicial object is Segal if it satisfies the analog condition. So if the value at an n is the same as the value on this simplicial complex, which spelling it out is really the same condition as before. So we take x at an interval over x at a point and so on, and we take this fiber product. So I will use this notation with valuing x on a simplicial complex because it will be very convenient for later. So I already want to highlight this in this case. Okay, and yeah, so the idea now is that if we're in this homotopy coherent setting, then these maps, they're no longer required to be isomorphisms, but only weak equivalence if you want. But and so if we choose some inverse in let's say in the homotopy category, then we will have a diagram here which will commute up only up to some specified homotopies, and these homotopies this diagram will still commute up to specified homotopies, which will be sort of the structure encoding this associativity. And then similar such diagrams, which one can write down, will encode compatibilities between these associativities. Okay. And of course, one of the main examples is the model of infinity categories themselves, where we can encode an infinity category as a Segal simplicial space with some additional completeness condition, which somehow tells you that the invertible morphisms are the ones you would like to have. But this is not so important for this talk. So let me give you one example, which will be somehow will motivate what will come also in the future. So one nice such Segal simplicial set comes as follows. So this is the original construction due to Segal to get cohomology theory. So imagine you start with some additive categories, for example, projective modules over a ring. Then you can get a simplicial object in, let's say, groupoids, or I guess you could, yeah, you could put some target here depending on exactly what you're doing, but let's say groupoid for now, which sends n to the following thing. So n, you choose n many, yeah, maybe I should have said this, that this goes up to an. So you take n many objects, you take n many objects in your category together with choices for direct sums of these objects. And of course, these choices will be canonical, like there will be a contractible space of such choices, but let's say you fix some, and this will give you an actual simplicial groupoid, which will then satisfy the Segal condition precisely because this additional choice of this sum is somehow going to be immaterial. And in this case, it turns out that you can actually lift the simplicial object to gamma because you can permute these AIs however you want. So this gives you some action of the symmetric group, which will then actually lift this to gamma. So you actually get a Segal gamma space, if you want, which is just another name for maybe what is usually called a special gamma space. And from this, you can get K-theory by passing to very special or by group completing, depending on your perspective. Okay, so this is an example to keep in mind because we will now see a slight variation of this example. So when we pass to two Segal objects. So let me now put it up here so that you can see it. So two Segal objects, we kind of want to do something similar, except that now we go in a situation where the multiplication, composition, addition, however you want to call it, the binary operation we're talking about is no longer uniquely determined. And one example which I find very nice is the one of extensions of modules. So if you have a module A and B, before we took their direct sum, and this is somehow a unique way of composing them. But now we might want to look at all possible extensions or short exact sequences, however you want to call them, of B by A, which I'll just draw in such squares with this decorated square in the middle. So each possible way of extending A by B, we could call a product of A and B, just that now there's many and not just one. In fact, there's a whole space of such, which are parametrized exactly by these short exact sequences. And while this is no longer a well-defined operation, it is actually still associative in a certain sense. So if you look at the following thing, so if you start with three objects A, B, C, so let's say A, B, C, you can do the following. You can consider the space where you first extend A and B by E, and then you extend the result E by C, or I guess one would say C extended by E, and then you get F. Or you can do it the other way around. You start with C and extend it by B, so you get G, and then you extend it by A further, and then you get F. So these are the two different ways in which you could like this associativity. And in fact, these two groupoids, if you want, are actually equivalent to each other. And in fact, they're both equivalent to somehow a more unbiased version where we would put in all possible extensions in a shape like this. And so, for instance, how would you, if you have this diagram, how would you recover this G? Well, you could define G to just be the quotient of F by A, or equivalently this push out here. And the third isomorphism theorem will then tell you that this G will in fact sit in a short exact sequence as indicated below. And somehow the dual version will give you an equivalence on the other side, where somehow you do the same thing on the other side. So you have these two equivalences, and somehow these two equivalences show you that you can go from this description to this description, therefore having some sort of associativity here. But yeah, but note that this is now multi-valued. And this whole data, just like before we could capture it in Segal's simplicial groupoid, we can now capture this whole data again in a simplicial groupoid called the Waldhausen construction, which looks like this. So now we send N to exactly these sort of shapes, which we have seen here, which are basically given by big collections of all possible extensions. So we start with these objects here, and then we choose repeated extensions until we fill this whole shape like this. And then by forgetting, yes, please.
Sorry, I think you maybe just moved on from your last comment, but what the situation of extensions that you mentioned before, like, would you be mentioning this with interest to, for example, Hall algebras, or is this more tangential?
No, this is exactly, I will make a remark about this later, how you can actually get the Hall algebra from this perspective. I will say this in 10 minutes.
Okay, then I'll wait. Thank you.
Yes. So you can package this in a simplicial object, whose cells look like this. So note that at the value 1, we will just get a single object. At the value 0, there will be nothing. There will be just a 0 object. And then at the value 2, we will exactly get short exact sequences. And and now this will be a simplicial object valued in, and now this will depend exactly what you're doing. Like sometimes it's a groupoid or a space, sometimes you have a stack or a category. It really depends a little bit what is the object which parameterizes these things. And it satisfies this condition, which is sort of the one which I've written. Oops, why isn't this condition here, but now written abstractly? The value down here is exactly the value on the simplex, and we have these two projections which correspond to two halves of the simplex, which are the two sides of the associativity equation. So you see here you have A, B, C, a product of A and B, and then a product with F. Here you have the other side, and here you have some of this unbiased version. And this will lead exactly to the two Segal conditions, so formalizing this notion. So I will not write the exact definition now, because I will do that more generally later, but two Segal objects are objects from delta, are simplicial objects like this, which satisfy this condition, and then higher versions, which I will write down explicitly later when I come to cyclic polytopes. And now I come to the remark about Hall algebras. So if you're given a two Segal object like this, so which you really should think about a multi-valued monoid, you can take some suitable linearization or cohomology procedure, which you think as a functor from C to vector spaces, modules, or whatever, which has suitable backwards and forwards functorialities. And you can consider a sort of convolution algebra where if we think of an element of this as some sort of cohomology class, which we can evaluate on something here, like this could be, for instance, functions to some ring, but also it could be some more complicated cohomology class, then we can write this sort of convolution product here where we integrate. Of course, what this exactly means depends on what your cohomology theory is, but usually maybe there's some notion of integration, and you integrate over the space of all possible choices where you write A as a product of A by B, and then you evaluate add from A and G on B. So you really see this is a convolution product. And the fact that this multiplication here does not have a unique output doesn't really matter because you're parametrizing over this whole space anyway. And formally, you would look at this span, and then you would pull back along the first map and push forward along the second map. And of course, you will need some axioms on your cohomology theory for this, but I don't want to really go into this. And now comes the remark which a person asked before. So if we do this for X being this Waldhausen construction, then these are exactly Hall algebras. And now again, there are many different types. Like there's the classical one, there's motivic Hall algebras or cohomological Hall algebras. I mean, they all arise in exactly this way by taking this convolution algebra for some suitable Waldhausen construction. Okay, so before I move on to general Segal spaces, I just want to mention something because so let me keep this maybe let me keep this one up here, and let me just say something, because this is we saw in Ike's talk the category of trees, and I won't spend a lot of time on this, but I just wanted to quickly mention that there's actually a close connection between two Segal objects and these trees. One can actually encode two Segal spaces also in the terms of dendroidal considerations. And so Ike explained to us that there's this leaf functor which takes a tree and sends it to its set of leaves plus a base point. I mean, he was thinking of this as partial maps. I think of it as pointed spaces, but it's the same. And there's a similar planar version where if you take a planar tree, which let's say like this, then if you look at a planar tree, remember it has a distinguished root, then it will partition, if you think of these edges as like going to infinity, then it will partition the plane into areas, and these areas are canonically or linearly ordered. And so you can think of this as a linearly ordered set in delta. So you will get this functor like this. And now here is one of the first results in my PhD thesis, which is that these two functors, they're actually localizations in the infinity categorical sense. So I mean, it's easy to see that they're one categorical localization, but they're actually also infinity categorical localization. And what this means is the following, that if you look at functors, so if you look at functors from, let's look at the plane version. The other one is exactly the same. If you look at dendroidal objects, you can restrict to simplicial objects. And in fact, this restriction is fully faithful. And the essential image can be described by what I call invertible dendroidal objects, which essentially arises by localizing at the inner edge constructions. So Ike explained to us what this is. So basically, you are allowed to take some arbitrary tree, contract all inner edges until you're left with a single vertex. And if you localize at these morphisms, you will exactly get the simplex category. That's somehow interesting, right? Like usually if you do an infinity categorical localization, it will be an honest infinity category, but now you actually get back a one category. And maybe we will actually see tomorrow or something in Walker's talk, some versions of these considerations of why sometimes one actually gets a one category back from localizing, because this is, of course, usually not true. And Ike also explained to us that in the dendroidal objects, there are the so-called Segal objects inside, which up to this completeness condition, which again, I will suppress, correspond exactly to infinity operats. And now if you take the intersection of these two classes, so if you take the Segal objects, which actually are in the essential image, then these correspond precisely to the two Segal objects on the other side. And so essentially what this says is that two Segal objects can be seen as a full subcategory of the category of infinity operats of those which I will call invertible infinity operands. And as a consequence, one also gets, if you restrict further, so inside the 2 Segal, you have the ordinary Segal. And if you further put the condition that the value at 0 is a point, then you get exactly the analog of the special gamma objects, if you do this in the case for gamma. And on the other side, this really restricts to what Ike was calling covariantly fibrant dendroidal objects. So so here, as a consequence of this localization result, you also get this result which Ike mentioned. And then, of course, you could localize further to the very special model structure if that's what you're interested in. Okay. A final remark. Walker-Stern also has a different characterization of 2 Segal objects, which you can characterize as certain algebras in the category of spans. And this is another way of formalizing the sort of multi-valuedness of the composition. Okay, so I will now move on I leave the theorem up in case somebody wants to still look at it. And I will now move on to the more general setting, namely about higher Segal objects. And I will be following the paper of Dikov and Kapranov, where these objects were first introduced, and some parts of this were worked out then in more detail by Burgundke. And I will now explain how one defines these higher Segal objects. So we have seen Segal objects and 2 Segal objects, and so far it's not completely clear how these fit in a bigger hierarchy, but they do as follows. So consider the moment map in RD. So it's just a map which sends T to this vector of all the powers. And there's these so-called cyclic polytopes, which are defined as the convex hull of, you take some finite set, let's say for simplicity 0 up to n, you apply the moment map, and then you get some points in R to the D, you take the convex hull, this will be a convex polytope. And these are actually very combinatorially interesting polytopes. Yeah, I don't want to say too much about this, but let's draw some pictures. So if we look at D equal 2, then we just have a parabola. And if we choose some points on the parabola and you take their convex hull, you just see a polygon specifically an n+1 gon in the plane. So this will be the cyclic polytope C4-2. Okay, let me now scroll up so you can keep this one here. And so if these two numbers agree, then you will always just get a simplex, because you will exactly get a D+1 many points, which are sort of linearly independent, so they will really span a simplex. And one example here, now, of course, the drawings get less visible. So this is now supposed to be a 3-dimensional picture. You have this moment map like this, and if you take 4 points, you will really get a 3 simplex, as indicated in this picture. The pictures, one has to sort of see it. Of course, higher dimensional pictures become very hard to draw. So as I said, these have very rich combinatorics, but we will need a couple of facts, which I will recall. So if you look at the boundary of these polytopes, so this will be a D. So since we start with a D+1 here, this will be D-dimensional objects. And in fact, it turns out that these boundaries decomposes into 2 pieces called the upper boundary and the lower boundary. And the upper boundary somehow intuitively is what you get if you look from above onto your polytope, and the lower boundary is what you get from below. So the formula is not so important, but like, for instance, in this case of the tetrahedron, you can sit down here and look up, and then you will see some 2-dimensional shape, or you can look from above and you will see something different. And the main thing is that these 2 things, they're actually simplicial complexes. So let me highlight simplicial complexes. They really consist of simplices. Their facets are really simplices. And if you project down, so if you just forget the last component, then you will get the cyclic polytope of the dimension 1 lower. And so therefore, this simplicial complex will induce a triangulation on this polytope, because this simplicial complex comes with a subdivision into simplices. Let me draw a picture so you can see what I'm talking about. So if we look again at our polygon here, if we sit downstairs, then if we look up, we see the simplicial complex, which looks like this. And you see this decomposes the interval into a lot of small intervals. If we look from above, then we only see this long edge. So we only see a single long interval. Similarly, if you look at, let me scroll down here so you can keep this definition up if you want to still look at it. Similarly, if we look at this tetrahedron, if we look at it from below, then we will see a square. I mean, it's a very distorted square, but like it's a fourgon with a triangulation given with this subdivision. And if we look from the other side, we will see this different subdivision. And this is not exactly called the 2-2-Pachner move, which interchanges between these two. And similarly, I will also draw later a picture, a three-dimensional picture. There I can no longer draw the actual cyclic polytope which sits on top, but I can still draw the two triangulations. I will show that in a minute. So, but with this, with these definitions, we can now actually come to the main definition of which I guess deserves being deserves being highlighted. So, so a simplicial object is called the following. It's called lower D Segal if the value of x on this lower triangulation, so remember this is a simplicial complex, so we can evaluate x by it, simplex by simplex, and then do the values together, if this agrees with the value on the whole simplex. And similarly, so if this map is an equivalence. And similarly, it's called upper D Segal if the same is true for the upper boundary. And then it's called D Segal if it is both upper and lower D Segal. And so there's a basic proposition which will not going to be so important for this talk, but just I just wanted to mention it because this is sometimes used as the definition. So this is again Dikov and Caprano von der Supergundke, but this heavily uses combinatorics of cyclic polytopes due to Rambau, which says that you can, if it is D Segal, then in fact this map will be an equivalence for all triangulations of this cyclic polytope for, I guess I should say, for all n bigger than D. So here we have two specific triangulations, but it turns out that if you just require these two and you require this for all dimension, it automatically implies the same for all triangulations. Okay, so let's leave this definition up and let's look at some examples so that we see what we're actually talking about here. So if we look at lower 1 Segal, so remember the cyclic polytope, the one-dimensional one is just an interval, and the lower triangulation just consists of subdividing it into all these small pieces. So looking at this simplicial complex. So we see that it's lower 1 Segal exactly if this map is an equivalence, which was exactly our definition of Segal. So this really recovers the notion of a Segal object. And for 2 Segal, we saw this 2-2-Pachner move, which was encoded by the simplex and its upper and its lower triangulation, which are this and this respectively. And so this is really the condition we saw before for 2 Segal conditions. But now we see that more generally from this proposition, we will get that x evaluated at any polygon with any choice of triangulation. So here I've sketched one, but you could choose any different one. For any choice of triangulation of the n-gon, this map will be an equivalence. So let me just draw, I promised to draw a 3-dimensional picture. So as I said, here I cannot draw the 4-dimensional polygon of which these are the boundary, but I can just draw this triangulation. So if you look at, let me zoom in just a little bit. So if you look at this, this 3-dimensional polytope, which is given by gluing together 2 pyramids on top of each other, this will actually be the corresponding cyclic polytope. There's one obvious triangulation, which just consists of the two pyramids themselves, but there's actually a slightly less obvious triangulation into 3 pieces where you cut in the middle along this a middle line through. So if I zoom in a little bit, you can actually see that if I take these pieces, I can sort of move them together like this to really form the shape I was describing before. So yeah, so and so this would be the 2-3-Pachner move. And so this this is the lower triangulation, this is the upper triangulation. Okay. So it turns out that one can actually explicitly combinatorially characterize these simplicial complexes. And in fact, this will, going forward, we will sort of forget about where these came from, and we will just keep around the combinatorics and see that this combinatorics can actually also be obtained in a completely different way, from a different type of analogy. Okay, so this is called Gale's evenness criterion, and essentially it amounts to computing some van der Monde determinants. And it looks like this. So let's consider first a case where D is odd. Let me actually put back the definition of this upper and lower boundary, just so. So if D is odd, so it's of the form 2k minus 1, in this case, we can write, so this triangulation, we just want to describe what are its maximal simplices, and there will be some subsets of n, and they're exactly those which can be written like this. So there are disjoint union of subsets of the form given by two consecutive elements, so ij and ij minus 1. And this union being disjoint just means that ij minus 1 has to be strictly, sorry, I messed this up, sorry. Like this, yeah. Anyway, so this union is disjoint. So let me just, an example, if we look at 4, so if we look at n equal 4, then what are the maximal simplices? They're listed here. So they consist of taking pairs of elements in all possible ways. So in this case, there's exactly 3 ways of taking 2. So the fact that we're taking 2 pairs corresponds to the fact that this is the 3-dimensional Segal condition, so k is 2. And then, so we're still in the case where this is odd. Now we can also describe the maximal simplices of the other triangulation in higher dimensions, so for D plus 1 and D plus 2, by the following procedure. So if we take a maximal simplex, we can adjoin an element at the end, so adding an element at the very end to all simplices, then this will give you exactly the maximal simplices of the upper triangulation. And if you adjoin an element at the beginning, it will give you the one of the lower triangulation. And then if you do both, you will get the, sorry, this is another typo. You will get the upper triangulation of the corresponding higher dimensions. So the upshot of this is that we really only need to understand this one, and then these other ones will follow automatically. So this is really the thing you should remember from this discussion, that we can understand very explicitly the odd ones, and that's sort of all we need to do. Like the lower odd ones have a very nice description, and the other ones then arise by attaching elements at the beginning and at the end. So this will, yeah, this is what you should remember from this. So as a corollary, so let me keep this up. So as a direct corollary, you can see that, for instance, if you want to know if something is 2 Segal, you can reduce it to the lower 2k minus 1 Segal condition by precomposing with this functor, which adds a vertex at the beginning and at the end, respectively. So it's 2 Segal if both of these path spaces, or sometimes called the collage, are the corresponding lower condition. Yeah. So let me just point out that there's a very nice class of examples which was worked out by Pogundke, which is called a higher Waldhausen construction. And these are examples of 2K Segal objects. And so these will be a bit like the Waldhausen construction, just that you have higher dimensional grids. And I won't say too much about this. I think there's going to be also more talks who will talk more about this, and where you will maybe see these graphs appear in more detail. So maybe I won't. Yeah, and the main thing is that they give you de-loopings of the K theory. Okay, so let's put maybe here, let's keep the main definition up. And now so what are we focusing on today? So as I said, the lower odd Segal condition are somehow the most fundamental in a sense, because all the others can be reduced to those via passing to path spaces. And so if we look at this hierarchy here of lower odd Segal, and then there's this related hierarchy of the 2K Segal, it turns out that actually subdividing this hierarchy in this way is productive, even though maybe at first it looks a little bit weird to separate the odds from the even in this way. But it turns out that this hierarchy on the left is related to a form of excision on the simplex category, and this hierarchy on the right is related to a similar form on excision, but now not on the simplex category, but on the cyclic category. I will say a bit more what the cyclic category is when I come to that point. So let me keep maybe up this slide now so you know what we're trying to do. So basically, the goal of this talk is to explain how one can conceptually understand this hierarchy of Segal spaces as some form of excision. And then it will be somehow a relatively easy corollary to pass to the even version by applying suitable path space criteria. And this will then lead to a similar story on the cyclic category. Okay, so I'll leave this one up on the left, and let's move on into some sort of interlude. And the interlude I want to do is I want to explain to you what manifold calculus is, at least in a very rough way, because this is somehow where the inspiration of some of this comes from. So somehow this has nothing formally to do with what I'm saying about Segal spaces, but it has a very close analogy, so to say. And I mean, I don't know exactly what the formal connection is, but it does inspire some true theorems. So I guess it is useful in some sense. Okay, so but let me tell you what manifold calculus is. So, so this is manifold calculus in the spirit of Goodwill Weiss. I think those names should appear somewhere, otherwise I should add them. Okay, so let man be the topological, or I guess infinity, if you want, category of smooth manifolds and embeddings between them. So if we, let's say we take a functor, a contravariance functor to some targeted C, we call it excisive if in the following situation, so if we have M covered by two opens, so let me say open cover, then we can compute the value at M by first computing the values on these two smaller pieces and then gluing them back together along their intersection. Or said differently, this square needs to be sent to a pullback square in C. And for instance, to illustrate, look at this manifold here. We can decompose it into two nicer or maybe easier pieces. And now if we know the value of here and the value here and the value on their intersection, we somehow can glue this value together to get a value on the big space. This is of course related to Meyer-Vietoris sequences. So for instance, if the target is some derived category or something, then after applying homology, you will get some Meyer-Vietoris sequence out of this. Okay, so the main example, which is often studied in manifold calculus, I only mention this for completeness, is the functor of immersions is excisive because being immersion is a local property. So if you want to take an immersion of this into some other manifold, then it's enough to give an immersion here, and a compatibility here, and it will automatically extend to an immersion. However, the same is not true for embeddings. Because if you have an embedding here and an embedding here, being an embedding is a global property, and the corresponding immersion which you get on the top might have some self-intersections now suddenly. So being the space of embeddings is not an excisive functor. And this is maybe the main example in this business. And so the idea is that if you start with some arbitrary functor like this one, which you're trying to understand, then it can be a good idea to interpolate between, so you have here the functor, the category of all functors, and here you have the one of excisive functors, which are also called polynomial of degree smaller equal 1. And then there's this filtration given by polynomials of degree smaller equal k. And I will say with the definition in a moment. And then there's a notion of approximation where every functor you can approximate it by higher and higher polynomial functors, leading to such a tower which in good cases can give you some information about the functor you care about from its polynomial pieces. So this is somehow the main idea. And let me tell you what a polynomial functor is. And here comes the striking thing. This definition, which works for manifold, we will actually be able to make sense of it in delta. So that's why I want to write this in detail. So a functor is polynomial of degree smaller equal k if it satisfies the following condition. Whenever we have an open cover, but this open cover is supposed to satisfy the stronger condition, which says that any two of the opens already need to cover the whole space. So this is equivalent to saying that the complements are closed and pairwise disjoint. This is how it is often phrased. So if we are in this situation, so we have these opens, then we can write some huge cube, which consists of M, it consists of all these U's, it consists of all their intersection, all their triple intersection, and so on. And at the end of the cube, you have the intersection of all possible U's. So this is some huge cube, and we want that our functor x sends this to a limit diagram. Or written slightly more compactly, the value of x at M can be written as this limit over all possible finite intersections. In this case, they're all finite, over all possible intersections of these UI. So here I drew a picture. So we have, we could take out this. So the open set would be the rest. We could, and then we could take out three disjoint closed sets, and then we would get a three-dimensional cube, and then the value of the big manifold would have to be assembled from these pieces. And actually, there's sort of a, not really dual, but like a different way of defining the same notion. So here, if you notice, we are sort of fixing the number of opens which we have. So here we really have only exactly three, or at most three opens, but the opens themselves can be quite complicated. And there is a sort of a complete opposite where we allow a huge number of opens, but we require these opens to be very small and very simple. And this is what's called a good K cover. So let me keep this picture up and let me give you the definition. So a K cover of a manifold is given by an open cover, not necessarily finite, such that each finite set of cardinality K, at most K, is contained in at least one of these. So it's not just every point is covered, but every collection of at most K points is also covered by one of the elements. So this is equivalent to saying that the Cartesian product of K copies of M is covered by the corresponding cover, where you just take Cartesian powers. And it is called good if additionally all the finite intersections are diffeomorphic to a disjoint union of at most K disks. So they're really simple. They're very easy to describe. They're given by at most K disks, and therefore they're somehow as simple as possible. So you really see this dichotomy. Oops, I didn't mean to erase that. You see this dichotomy here, where on one hand you have a small number of kind of complicated pieces into which you're chopping your manifold. And here you have a very huge number, but of very small and simple pieces, where all the intersections are also small and simple and so on. And there is this theorem by Boavida and Weiss, which says that these two give equivalent definitions for polynomial functors. So a functor is polynomial of degree smaller equal. Sorry, this should be a D, not a K. It's a polynomial of degree smaller equal K if and only if for each good K cover the value is given by the limit over all these intersections of this cover. And we would say that it satisfies the send, or one sometimes would say it's a sheaf with respect to these good K covers. Okay, and let me just sketch this lemma that every manifold has a good K covering, and you will see in a moment later why I'm doing this. The reason is that this will inspire a certain analogy on the delta side. So every manifold has a good K covering, and the idea is just, if you take any set which has cardinality K, we have to cover it by some open. Well, what do? We have this set of points. Well, we just choose very small open balls around each. So we choose very small open balls, and then take the union of those balls as one element of our covering. So this way we just by construction have covered every K element collection. And in fact, this will be a good cover if we make sure that these balls are somehow convex with respect to some metric, but they're supposed to be very small, very simple, very convex balls. Okay. So let's go back to the simplex category. Let's keep this definition up and let's go back to the simplex category. And now comes somehow a little bit of fantasy math. So I'm going to try to sell you some snake oil and try to sort of give some, I try to pretend that the objects in delta are manifolds, even though of course they're not, but somehow this analogy will lead to some interesting comparison. Okay, so let's pretend that an object n is a manifold, and I'll put everything which is somehow fake math in quotation marks, just to be safe. And let's pretend it's a manifold which has the following points. So a point is given by an adjacent pair of elements. An open set is given by just a subset of n. And we say that a point lies in this open set if it is contained as a subset. So note that an open set might contain no points. So for instance, if we take just a single element as an open, then it contains no point in this sense. And we say that two open sets cover the manifold if each point of the manifold lies in either one or the other. I mean, that's sort of the obvious definition of cover, but note that this is not the same as saying that they're the union, that their union is n as subsets. So as an example, let me provide you with this open cover where we have, this is our manifold, we have these two opens, and somehow their union is n, but the point 2, 3 lies neither in I nor in I prime. So being an open cover is a bit more than just having their union be the whole. Okay, so let me keep this one up so you can ponder this, and let's try to now. Yeah, and I also have a picture. Let's see if I can fit it. Yeah, I can fit it on the screen here. So we can picture it like this. Our manifold has these green points, and then the open sets somehow look like this. Okay. So now let's actually do some actual definitions which are inspired by this heuristic. So the first observation is that the definition of polynomial functors, we can copy it verbatim now. We can say, well, we call a collection of subsets, we call it compatible if for each I, there is at most one index such that this point does not lie in here. So this is really the same as saying that if each two of these are an open cover of the manifold. So for each two, there's at least one of them which contains a given point. So that means that any given point must be contained in all except for maybe one of these. So this is now this definition. And now with this definition, we get this following theorem. So this is now an actual theorem, which says that a functor is lower 2k minus 1 Segal if and only if it is a polynomial of degree k, smaller equal k, in the sense exactly as above, that the value on n can be computed as this limit over all possible intersection whenever we have such a compatible cover as before. So this is really the analog of being polynomial for manifold calculus. And now I will explain how this lower Segal condition, you can think of it as sort of the other end of the spectrum with good k covers. So let's keep this up here, or let's do it like this. So recall the construction of good k covers. What we had to do is, if we're given k points, let's say these, we had to, for each of these points, choose a very small open around it and then throw the union of those opens into our cover. And now we can just take out a tautological thing, because each of these points has somehow a minimal open which contains it, which as a subset is really just a point itself. This is somehow maybe a bit silly thing to do, but we can get an analog of a canonical good k cover by really just for each k many such points, taking the union of these subsets here. And we can, let's say, make this union disjoint just to make sure we don't, to not have any redundancy. Like if the union is not disjoint, it will always be contained in something where the union is disjoint. And now, if you remember, these were exactly the maximal simplices of this triangulation. So this is how somehow we come back full circle, and we see that we could have invented Segal objects without knowing about cyclic polytopes at all, just by doing some fantasy math with manifold calculus, and then inventing this sort of definition of a good cover. And then it would sort of lead back to the definition of a higher Segal space without ever mentioning cyclic polytopes at all. And so this theorem here can be really seen as the analog of the theorem of Boavida and Weiss, comparing polynomial functors, so comparing sheaves with respect to these subdivision into k+1 pieces on one side, and sheaves with respect to good k covers on the other side. And this is really sort of the analog of this. So let me keep the theorem up, and let's show some examples of some of these covers and how they look like. So let's look at the easiest example, k equal 1. So let's take n equal 2. A good k cover, it consists of taking all the possible pairs. We have k equal 1, so we only take a single pair. And in this case, there's a unique one. And actually, there's also a unique compatible cover. So in this case, these two agree. And this will always be like this. In the first non-trivial dimension, these two things will agree. And now the next cover here, you see, on the right side, we just keep adding more and more of these pairs. And you see that this is exactly, descent with respect to this cover is exactly the Segal condition. So we're saying that the value on n can be glued by the value on these very small pieces with respect to their intersection. And on the left side, there's now suddenly a very big number. Like I've drawn the three of them for n equal 3, and already for n equal 4, there's many more, so I didn't draw them all. But if you turn your head like sideways 90 degrees, you can maybe read what I wrote here. But essentially, on this right side, you see that the size of each open remains constant and is very small, but the number of opens keeps increasing. And on the left side, the size of each open is potentially big, and this will in fact be even more prominent for a higher k, but the number of opens is fixed. So this somehow we have, again, this dichotomy, which we had for manifold calculus. And here I drew the corresponding table for k equal 2. So I won't spend too much time on this, but you can again see that in the first non-trivial dimension, these two agree. And then the Segal cover is this one, which has all possible ways of taking two pairs. And then for n equal 5, I think in this case it's all of them. But you see that on the left, the number gets very big, very fast, and there's a lot of them. So yeah. And again, you see this behavior that here the number of sets is fixed, and here it gets bigger, and then conversely, here the size gets bigger, and here the size is fixed. Okay. Yeah, let me just keep this theorem up. So on one hand, we have this lowercase Segal, which maybe we might argue we can be interested in. So maybe the question which you might wonder now is, what's the meaning of this condition, right? I mean, I have somehow introduced it in this way by this informal analogy, but actually it turns out that this has a very concrete meaning in terms of category theory of the simplex category. And this is what I want to explain next. So what is the intrinsic meaning of such a compatible collection? So recall, compatible collection was this analog of these k-fold covers from manifold calculus. So if let's look at the simplest case, k equal 1. If we have such a square given by two subsets I0 and I1 in n and their intersection, there's the following lemma, which is not that hard to prove using basic properties of the simplex category, that these two I0 and I1, they are compatible if and only if this square is a push-out square. And somehow the idea is actually quite simple. I mean, this is, if we just forget the linear ordering, then this is clearly a push-out square Sorry, I should have, of course. Yeah, so in the definition of compatible, I should have, no, sorry, that's no, never mind. So as sets, N is covered by these two. So clearly, if we forget the linear ordering, if we have two maps like this, they will glue to a unique map out of N. And the question is about the linear order. And the fact this compatibility tells you precisely that whenever you have I smaller equal I plus 1 in here, then this comparison will lie either here or here. And so the glued map will also be compatible. And so from this you will get that this is a push-out square if and only if this is compatible. So this is somehow already a hint of the meaning of this compatibility condition in terms of the categorical property of delta. And note, and this will be relevant later, that this square is always a pullback square, just because somehow this intersection is exactly the pullback of these two in delta. But so now we might wonder, okay, what about other pullbacks and pushouts in delta? Let me scroll up, or yeah, let me keep this here so you can still look at this. Let me scroll up here. So let me propose you the following two squares, which are now given by, which include the degeneracies. So I hope this notation is clear. So this is a linearly ordered set just by reading left to right. And this map sends 0 and 0 prime to 0. It's like a co-degeneracy map, and the same here. So this left square, it actually is a pullback. And this one, for instance, is not a pullback. And in fact, if X is Segal, let me show you these two squares here. If X is Segal, it is in fact true that it will send this square to a pullback square. And so if you really think about what this square is encoding, what you're saying is that if you have a triangle, so a triangle here, whose restriction to 0, 0 prime comes from here, so that means it's degenerate. So you're saying you have a triangle whose first edge is an identity, essentially. It comes from a degeneracy. Then the whole triangle is degenerate, so it comes from this degenerate, which tells you that F and G are actually equal. So this you can really read as a unitality, where you say, if you have a composition of E composed with F is equal to G, if E is the identity, then F and G have to agree. So this is, of course, true in a category. And in fact, it also follows from the Segal conditions. But the second square is not necessarily sent to pullbacks by Segal spaces. And yeah, maybe I'll skip the argument for this. It's not so important. So the upshot is this, is that it's not just true that every square, which is both a pushout and a pullback, gets sent to, sorry, not every square which is a pushout gets sent to a pullback by X, but in fact, the following is true. X is Segal if and only if it sends to pullbacks, not all pushout squares, but only those which are both pushout and pullback. So this is what I will call from now on bicartesians. A bicartesian square is one which is both pushout and pullback. So you saw that, for instance, this one, it fails to be a pullback. This one might sometimes fail to be a pushout. And somehow if we take both conditions together, this is exactly the right condition. So a Segal object is exactly one which sends all bicartesian squares to pullbacks. And more generally, the theorem which I will now state will essentially say the analog version, but for higher dimensional cubes. So let me just introduce some terminology. So if we have a cube, which we can think of as a functor from the power set poset of some set S, is called strongly bicartesian if every two-dimensional face is bicartesian. So every two-dimensional face in this huge cube is both a pushout and a pullback. Equivalently, you can formulate this by saying that it's a right can extension of its end and a left can extension of its beginning. So here I have a picture. So if this is a huge cube, you have this initial piece and you have this end piece. And if you start from the initial piece, you can get the rest just by iteratively taking pushouts. Or if you take the end, you can get the rest by iteratively taking pullbacks, and both of these procedures should give you back the cube you started with. So this is the higher dimensional analog of being a bicartesian square. And now comes the observation. Let me keep the definition up. So the observation is that if we have a cube, which is described as an intersection cube of some subsets like this, so it's given by sending, for convenience, I label it by op here, but basically you send J to the intersection of all, to the corresponding I. So this is really the cube given by taking these I's and all possible intersection with the convention that the empty intersection is just n itself. So at the top vertex of the cube, we put n itself. Then this is strongly bicartesian if and only if this collection is compatible. So which, recall you again, just meant that each of these intervals belong to at most one of these. So this gives an intrinsic meaning to these compatible collection. They are precisely those intersection cubes which are strongly bicartesian. And from this observation, we actually get somehow the main theorem of this talk, which is the following, which says that the following are equivalent for a simplicial object. X is 2k minus 1 Segal. X is polynomial of degree smaller equal k. So this part we kind of already saw before. So this means that it sends strongly bicartesian intersection cubes are sent to limit. So remember, strongly bicartesian intersection cubes are exactly those which are given by these compatible collections of subsets. And now this is also equivalent to saying that it sends all strongly bicartesian cubes to limit cubes. And you see that this last condition, this is now a condition which is purely categorical in the sense that we have just characterized by universal properties those cubes which are supposed to be sent to limits. So now there's no more arbitrarily choosing some collection of maps given by some external combinatoric. This is somehow very intrinsically given inside the category delta. And just a side remark, so I call this X satisfying this condition, I call it weakly excisive, or I guess weakly K excisive for K. And you should compare this to Goodwillis calculus of functor when one says that X is K excisive if it sends not strongly bicartesian, but strongly co-Cartesian cubes to limit diagrams. So strongly co-Cartesian means that every two-dimensional phase is a push out. So this is a little bit different from that, but it has some similarities. Okay, let me make a remark about what the relationship between these two is. So here we have all bicartesian cubes, and here we only have those which are given by intersection, so only those whose maps are injective. And in fact, the relationship between these two is very analogous to the passage between what are called two Segal objects and so-called unital two Segal objects, where the two Segal condition, they only involve diagrams with injective maps, and the unital two Segal object condition, it also involves some degeneracy maps. And the fact that these are equivalent, which was proved by these people, is in fact a version of somehow this equivalence, where somehow we're passing from only a certain class of squares with injective maps, which are bicartesian, to all possible bicartesian cubes. Yeah. Okay, so I leave up the main theorem here, and let me now come to the last part, which will I won't be as detailed anymore, but I just want to somehow so far we have talked about this is also I should have said lower. That's the one we are considering here. I apologize for this. Lower. Okay, so we said in the beginning, remember that we were interested in two classes, the lower odd ones and the even ones, because those are somehow the ones which seem to appear in nature. At least that seems to be what's happening. And so, and it's those for which the first level of the hierarchy is best understood and somehow seems to be very interesting. So what about the even ones? And so in particular, you might wonder about what about two Segal ones? And so to study two Segal ones, let me remind you what the cyclic category is. So the cyclic category is the category of cyclically ordered sets. So a cyclically ordered set you can picture like this. It has a non-zero number of elements, and they are no longer linearly ordered, but they are cyclically ordered like this. And there are many ways to make this precise, but one way, for instance, of saying what the morphisms in these categories are to say we take the circle with n+1 marked points and the circle with m+1 marked points, and then we take maps which are monotone, so in the sense that if you go along the circle in the source, it also goes correspondingly along the circle in the target. They're monotone, they're of degree 1, so they'll go around the circle exactly once, and they need to send marked points to marked points, so that's indicated by the fact that it goes from this pair to this pair. And then you take these up to homotopy. That's one way of defining it. You can also define it purely combinatorially in terms of just these cyclically ordered sets. Just an example, maps in lambda from n to 0. So 0 is the cyclically ordered set which just has one object, which is somehow cyclically ordered to itself in a sense. A map from here to here, it needs to collapse almost all of the arrows to this point, and then one of these edges gets sent to this edge. So such a map amounts exactly to giving a linear order on n compatible with the cyclic order. So like if you think of this as cutting open this circle here at this red place, then you really are left with a linear order like this. And from this, it follows that delta is really just a slice over in lambda over this object 0, where you send a linearly ordered set n to the corresponding linear cyclically ordered set n together with this map which cuts open exactly at the arrow from n to 0. So that's somehow the last arrow which would go back. Yeah. Another important feature is that lambda is self-dual, where you can exchange vertices. So if you have this picture, you can exchange the vertices and the arrows in this picture, like every vertex becomes an arrow and vice versa. And this will give you a self-duality on lambda. Okay, so let's keep this up so that you can see the definition of lambda. And now let's look at the following square. So you see this square, which I've drawn now with these arrows a little bit more explicitly than before. This is the one which encodes the one Segal condition, or it's one of the ones which encodes the one Segal condition. And it is bicartesian in delta, as we saw, but actually it fails to be a push out once we interpret these linearly ordered sets in lambda. And the reason, so one way of showing this is that, for instance, if you take this and you map into 0, then remember mapping into 0 just means giving linearly ordered sets compatible with the cyclic order. So and on this, so on this set here, or on the corresponding cyclically ordered set, rather, I should say, there are exactly 3 linear orders. Here there are 2, here there are 2, and there's a unique one here. And so there's no way this diagram can be a pullback, because this set has 2 elements, this has 2 elements, but this has 3 elements, this has 1. So this would have to be the Cartesian product of these 2. Yeah. So if this was a push out in lambda, then mapping into 0 would be a pullback, but it isn't, just due to cardinality reasons. Yeah. And so this motivates the following theorem, which is somehow the last theorem of this talk, which characterizes the even Segal conditions. And it says, well, okay, X is 2k Segal if it is what I call weakly excisive with respect to this inclusion functor from delta to lambda. And what does this mean? Well, it means that X sends to limit diagrams in C, not all cubes in delta that are strongly bicartesian, but only those which remain bicartesian once you pass to lambda. And in fact, this is the same as just saying those cubes in delta which are strongly bicartesian in lambda. That's, you can somehow forget about they will then be automatically already bicartesian in delta. So that's what I'm trying to say. So really we have this weakly excisive condition where we look at excisiveness, but with respect to somehow this, it's somehow a relative version where we let this functor guide us in telling us which cubes we're supposed to consider. And a corollary of this is that if you have a cyclic object, so a cyclic object is a functor from the cyclic category, which is 2k Segal, by which I just mean that its restriction to delta is 2k Segal, then this here is 2k Segal if and only if it is weakly k excisive. In particular, for k equal 1, we recover that a cyclic object is 2 Segal if and only if it is weakly excisive. And so this somehow gives it a very somehow very intrinsic meaning when we're talking about the cyclic category. And this is somehow no coincidence, because many of the applications of 2 Segal objects, they really take place in the case where one has cyclic 2 Segal objects. For instance, if one wants to build invariants of manifolds out of 2 Segal, of surfaces, of marked surfaces. Yeah, so you really see that in the case of the cyclic category, this is a very natural condition. So let me leave this theorem up on the left. And now I have 5 more minutes. Let me maybe, I wanted to briefly say some key ingredients of this, but maybe let's maybe skip this. Let me just give some final remark and some outlook about similar things which you can do when you're in some simpler situation. So you can considerably simplify this whole story if you assume that the target is additive. So, you know, it's either an abelian category or a stable infinity category or some suitable subcategory of those, any sort of things where which are suitably additive. And then I guess there's also this technical condition called weakly idempotent complete, but let's not worry about this for now. And also one can sort of work around this in some cases. But the point is that in this additive situation, one has access to a very powerful tool, which is the Dalt-Kahn correspondence, which was also part of my thesis to sort of extend to this general setting, which gives you an equivalence between simplicial objects in C and coherent chain complexes in C. So here one has to say what it means to give a coherent chain complex and so on. But this is then an equivalence. And now under this equivalence, this if I scroll back to these hierarchies here, all the way at the beginning, yeah, not all the way, these two hierarchies. So these two hierarchies, they somehow become the same hierarchy now. They collapse to each other. And so an object here is lower 2k minus 1. Sorry, again, I forgot to write lower 2k minus 1 Segal, if and only if it's 2 Segal. And you can characterize this in terms of the corresponding chain complex on the other side by saying that it is k truncated. So it only has values 0 up to k, but then only zeros. There's nothing afterwards. One more remark, which I don't have time to really expand a lot upon, is that if the target is additionally presentable and stable, the main example, of course, being spectra, then one can relate 2k Segal, or as I said, I mean, this is equivalently lower 2k minus 1 Segal, because of course it is going to be additive. You can relate these Segal spaces to excisive or k-excisive functors from the category of pointed spaces to C. And here now I really mean k-excisive in the sense of goodwilly. Yeah, so, but this is a story which I don't really have time to tell. And somehow this involves a version of this Dalt-Kahn correspondence, but for gamma instead of for delta. Yeah, I think this concludes my talk. So I will thank you all for your attention.
It's us who thank you, of course. Now we are for questions. Please turn your microphone if you want to ask.
I have just a question about the term bicartesian. So you said that you have you can construct these bicartesian squares in delta by taking iterative push outs. Is this correct?
Okay, so a square is called bicartesian just if it's
No, a cube. So if you have a cube, then you can construct it as an iterated push out.
Yeah, let me scroll back to this. Yes, exactly. So if you have this whole cube, inside this cube you have this initial part,
yeah,
and this terminal part. And so this whole cube is called strongly co-Cartesian if starting from this initial part, you can get the whole thing by left Kahn extension, which really amounts to just taking push outs everywhere. And it's called strongly Cartesian if starting from the end part, you can get it by taking pullbacks. And it's called strongly bicartesian if both are true.
Okay.
Does this answer the question? So this is really, it amounts to saying that every two-dimensional phase is both a push out and a pullback. This is the same.
What I wanted to say is actually, so my real question is the following. You have a functor from delta to gamma, so which was exploited by Segal in his paper.
Yeah.
And then instead of looking at your conditions in delta, you can also look at them in gamma. And there, so the condition I know quite well is this push out condition. And so you can somehow define gamma spaces which satisfy the condition that these push out cubes are mapped to pullbacks or homotopy to homotopy pullbacks, say. And I think that this should define some kind of model structure on gamma spaces, which gives you also k-excisive functors. But not all, only special ones. You see, everyone you have a gamma space, you can construct an endofunctor of base spaces in a canonical way. And this is used to construct the Segal spectrum out of a gamma space. So you have But now the stable model structure of Bausfeld-Friedlander, there you have quite a large family of weak equivalences, of stable equivalences, and somehow you can take finer model structures, and I think that you can use these push-out cubes to define the fibrant objects of this k-excisive model structure on gamma spaces.
Yes, so this is probably very similar. So you don't get all
you don't only get very special ones. So somehow connective. You only get the connective functor, the connective endofunctors, which is a very strong condition.
But so you're looking at
you have this k-excisiveness, which is precisely the fact that these push-out cubes are mapped to homotopy pullbacks. And
yeah, so you should note that in this last statement I was saying about Goodwillie calculus, I'm looking at a stable target. So so it would really be, for instance, pointed spaces to spectra. So k-excisive, there's this finitary condition, which just means that they commute with filtered colimits, but this is not so important. So if you take k-excisive functors in the sense of Goodwillie, from pointed spaces to spectra, then these can be described by the restriction to gamma, and then the restriction to gamma will be exactly this will be exactly these two Segal conditions.
Okay.
This is so maybe you were in the situation where the target is like something like pointed spaces. Then of course everything is more. Then of course everything is more complicated, and this no longer holds. So this really uses that the target is stable, which of course makes everything much simpler. Yeah. There's also a couple of questions in the chat.
Yeah, indeed.
Let me.
Question 1, actually question 2 has already been clarified apparently, but question 1 still waits for an answer.
Yes, question 1 is a good question. So let me scroll back to the. Just all the way here, the localization. So the question was whether this functor has an adjoint, and the answer is no. There is no functor on the one category level from here to here. So, I mean, if we had such a functor, then everything would be somehow, then it would be quite easy to see that this is a localization, but actually there isn't. So there is some sort of, so you can send, of course, each object n to the corolla, but this will not be functorial. So that's the, I guess maybe I can say something, a slightly refined answer. So let me just add a page here. So if you have a tree, which gets mapped to some n, so that means that these these are mapped by n, then if you now have a map from n to m, then you can always lift this map to some other, to some actual map in omega by just taking the inclusion of t into a bigger tree, where everywhere you graphed on corollas, and here too, according to this f. So these corollas here are you somehow look at what it has to be due to f, and so it's not really there doesn't really exist a functor in the other way, but there exists some way of going back, which is somehow exploited to prove that this functor is a localization. So you can lift arrows in a very canonical way.
I see. So philosophically, should I think of if there were to be a functor the other way, I should actually think of sending bracket n to like an infinitely large tree that doesn't exist in omega?
Yeah, I think that's reasonable, right? So an infinite tree, where then if you extend it, but I don't know, I would have to think about this. So there is an adjoint on certain comma categories, and this is in fact what gives you this localization result, which somehow is exactly what this here tells you, that if you fix, like if you look at, now I don't remember exactly, but there's, this is the main trick, because this gives you some adjoint on some comma categories, and then that gives you the localization. So then there was a second question.
Yes, so most of it was clarified, but can I ask a modified question too?
Yeah,
yes,
please.
of course.
So, of course, the power of good Willy calculus is that you actually have approximation functors.
Yeah, so these also, sorry, let you finish.
Oh, yes, I think you were about to answer, so please go ahead.
Yeah, so in this situation of delta, these actually exist. So, okay, let me say something about this. So let's assume that our target category has sufficiently many limits and colimits. Let's say it's presentable to be safe. Then these approximations will actually exist just due to formal reasons, because the simplex category delta is a small category. And so you're looking at diagrams from delta to C, let's say, and you want to force that a certain collection of subdiagrams get sent to limits. And you can always do this when this collection is a set. And this will be automatic because delta is a small category. So in this case, there's really, just from formal reason, there will be some approximation factor. However, what I do not know is a good procedure to actually calculate this approximation factor. And in fact, this is something I would really like to know, like how to compute the 2-Segal approximation of something. And I think this is this abstract result only gives you this existence, but it's really inexplicit. So it's very hard to compute.
But is it expected that something like the S dot construction is in the image of this approximation functor?
Well, the S dot construction is 2K Segal. So the ordinary S dot construction is 2 Segal. The higher S dot construction is 2K Segal. So it will be in the image of the approximation functor. Yeah.
Oh, of course, of itself.
This approximation functor is just a localization, right? So it will just on those things which are already 2K Segal, it won't do anything.
But I see. But there's no theorem to the extent that, like, if I start with some stable thing like C, or maybe even something that's not stable but has some, like, Waldhausen exactness, and I apply this, there's no theorem to the, stating that the S dot construction is the universal 2-Segal approximation is something derived from C.
Yeah, that would be very nice. I don't know of any such statement. Yeah,
okay.
That would be, of course, cool to know.
Thank you.
Okay, thank you very much. If there is no further question, maybe we have a 5-minute break and then we resume at 5. So thank you very much for the talk again.
Stop sharing then.
Yeah, I also stop the recording.